Good afternoon, everyone. So first of all, I want to acknowledge my two students, Yushin and Amr, who couldn't be here today because they have a tape-out deadline. But this work is all their stuff. Really, the focus of this work, is it too loud? The focus of this work is more, rather than looking at a specific hardware implementation for a specific task, we're going to look at the comparison of HOG features versus CNN features. So take a step back and look at the trade-offs between the two and understand where the energy differences are. Okay, so in our group, we primarily focus on video because we think video is the big data. We know that video dominates communication, so it accounts for 70% of the internet traffic. And then just the sheer amount of video that's being generated both for commercial as well as industrial applications is really growing to the extent that you can't have humans really look and extract information from the video. You need to do it automatically. In many of these cases, the video is going to be collected on battery-operated devices, for example, your phone, or even maybe a drone. And ideally, you'd like to do all of the processing there, whether it be for latency issues or privacy issues. However, due to energy constraints, what happens is we typically compress the video today and then send it to the cloud and process it on the cloud. And we know that even on the cloud, there are power constraints. So for example, these days you have to build basically a data center right beside a power plant in order to deliver all the power. So the main focus in my research group and kind of overlapping all these various different chips is going to be we want to enable energy efficient pixel processing. And one type of metric that we typically compare it to is video compression. That's because, as I mentioned, the default right now is to compress the video and send it to the cloud. And actually any image sensor you're going to have is going to have some form of compression on it. So if you're going to store or transmit video, you have to compress. And so what are the kind of budgets that we deal with when we're talking about video compression? First is the area cost, so that just the size of the chip really matters. So for example, in an ASIC, you might have only about 100 to 500 kilobytes of memory allowed on chip dedicated for this application, and you might have maybe 1,000 K gates. In addition, you have a very stringent power budget. So for example, in a smartphone, you have to operate below a watt. Often you have to do throughput, real-time throughput of 30 frames per second. And then if you work this out with HD, this ends up becoming about a nanojoule per pixel. And this is consistent across various publications, various standards, both encoder and decoder. So in this talk, we're going to take a step back. So one method that you do to extract information from video is through object detection or recognition. These are very simple tasks in computer vision that there's been a lot of research in this area over the past couple of years or decades. So there's two kind of traditional approaches that people do to extract meaningful information. For the feature extraction part, you have the handcrafted features, which are kind of, you have these computer vision experts that come in and tell you what to actually look for in the image to tell you meaningful information about this. And this was very popular up to most recently, like around 2012. And then what we had was learned features, where these actual features that are extracted are actually learned from the data itself. And this is where deep learning, convolutional neural networks come in. Often after feature extraction, you have classification. And classification is pretty much similar between the two. So the focus of today's talk and this work is on the difference between the feature extraction class. So basically HOG versus CNN. Okay, and the basis of this work is actually going to be derived from two chips that we've done within my group. These are both fabricated in 65 nanometer process technology, so these are all measured results. These were done by, Amr did the object detection HOG-based chip on the left-hand side, and then Yushin did the chip on the convolutional neural network. This is the Eyeriss chip that there's been some press about this recently. So you can see the sizes of the chip are about the same. We're going to talk about the K gates and the memory of the chips are still the same. So, assuming, PhD students around the same amount of time working on same process technology, both in my lab, how good can they do it for both of these chips, and can we compare and truly understand what's the differences between HOG and CNN? Okay, so just very kind of high-level overview of what HOG actually is. So HOG stands for Histogram of Oriented Gradients. So basically what we're looking at is you're extracting gradient vectors from an input image, looking at edges. You take a histogram of it, of the different angles, and then you do some normalization. It's a very simple feature, but it's been very popular over the past few decades. In particular, so we had built a chip back in 2016. This was published at VLSI that does object detection. And we were able to show through both joint algorithm hardware optimization that we in fact could do object detection at under a nanojoule per pixel right? And this is actually comparable to that video compression that we talked about before. So now for the same energy, to compress the video, you can actually understand the video. This was operating on an HD image, and you can detect multiple objects at the same time. So for example, cars and people at various steps. Okay, so we know that basically the message here is that HOG features are very efficient already, right? If you really squeeze the power. Okay, so what's been, very exciting for a lot of people these days is deep convolutional neural nets. So I'll do a very, very brief kind of overview, although I think most of you guys already know what it is. But basically, deep convolutional neural nets, basically what it consists of is several convolutional layers. Each of them extract features from low-level features going to high-level features. And these days, when we're talking about modern CNNs, we're talking between 5 to, in some cases, 1,000 different layers. And this is where the feature extraction is happening. And then you have fully connected layers, typically 1 to 3, and that's where the classification happens. But really what we care about is the convolution, because it accounts for the majority of both the processing and of the energy consumption. Okay, so that's going to be the focus of the CNN part that we're going to talk about. Again, I won't walk through the details of this, but really, convolution is not something that's new. We do that all the time in image processing for decades. What makes CNN challenging is the high dimensionality of the convolution. So it's not just a 2D convolution, but you have a third dimension, which is the channels, and then you also have multiple filters, and we're talking hundreds of filters that you apply. Okay, so the complexity really grows, and we can really see that in terms of, if you take AlexNet, for example, this is a network that was built by University of Toronto back in 2012. You can see that for various different layers, there's different filter sizes. The number of filters, we're talking about hundreds of filters, and the number of channels also changed. So the main things you have to account for in terms of hardware design is that the sizes of these filters are very large, and they vary with shape for different layers. We're talking about hundreds of thousands of weight parameters, and then hundreds of millions of multiplies and accumulate, right, per layer. So there's a lot of really heavy computation. Okay, so however, there are some properties that we can leverage. For example, it's very highly parallelizable, right? So all these things is just a convolution, just multiplies and accumulate, nothing special. So high throughput is possible, but the one challenge, both from a throughput and from an energy point of view, is the memory access, right? So every single time you do a multiply and accumulate, you need 3 inputs and 1 output, right? So your inputs are your filter weight, your image pixel, your partial sum, and then your output would be your updated partial sum. So the ratio there of reading and writing and access is very high. In addition, for the worst case scenario, data movement is actually very expensive. So if you were to read this, and you would never do this, but this is absolute worst case, you'd come from the DRAM, one read from the DRAM is 200 times at least higher energy than the actual computation itself. Okay, so we're talking about 4 to 1 in terms of the ratio of numbers, and then in terms of energy, we're talking about 2 orders of magnitude. In particular, there's 2 kind of architecture paradigms that you can use for high parallelism. So on the left-hand side, you have this temporal architecture, which is very popular in terms of GPUs and CPUs. The idea here is you have a bunch of ALUs, they share the same control, and they share the same storage. Okay? Alternatively, you have a spatial architecture, which is closer to what we like to do for the Eyeriss chip, and the main advantages are here. First of all, your storage is actually split across all of the different processing elements. So each processing element has a really small memory locally, and by small I mean 0.5 to 1 kbyte. So this is very tiny, and we also split the control across all of them. All right, and so as a result, each of these elements can actually also share data as well and operate autonomously, right, not in lockstep. And the reason we do this primarily is because data movement is expensive. So you may have all heard this before, but I just want to emphasize in terms of how expensive it actually is. So for example, if you do a multiply and accumulate in your ALU, it's 1x. If you read from a very small memory, so this is why we kept that memory locally very small, 0.5 to 1 kbyte, it's also 1x in terms of energy. If you read from your neighbor, sharing with your neighbor is nice, it's 2x, a little bit more expensive. If you go to a large global buffer, which is about 100 kbytes or higher, talking about 6x the energy. And then if you go to DRAM, of course, as we mentioned, it's 2 orders of magnitude higher energy, right? So we really want to have a data flow that minimizes or utilizes the lowest levels of the hierarchy as much as possible. I won't go into the details of it too much because we don't have time, but if you guys want to know, you can look at the ISCA or ISSCC paper. But the main idea is that we have some row stationary data flow that allows you to really leverage these low levels of the memory hierarchy. And then we also exploit sparsity in the activations. There's this nonlinear function that creates all these zeros, and as a result, you can do compression and skipping to save data movement and operations. And then this is the Eyeriss chip, so maybe I'll just keep moving forward. And in general, with the results of all of this, Eyeriss, I don't think I say it here, but it's around 278 milliwatts, and so it's about 10x more energy efficient than a TK1. Okay, so this is all kind of review existing work. If you want to know more, you can do a deep dive and look at the papers. But what we really care about now is the comparison between these two pieces of work, right? So the first thing, what we care about, we compare energy versus accuracy here on the scale. So note this is linear scale on the x-axis and exponential on the y-axis. And what we can see is that with HOG, already it's lower energy than video compression. But for both AlexNet and VGG, and these are measured results on the Eyeriss chip, we're looking at orders of magnitude, either 2 orders or even 3 to 4 orders of magnitude higher energy per pixel compared to HOG. And this is for kind of a 2x, a little bit above 2x increase in terms of accuracy. So for a linear increase in accuracy, we have an exponential increase in energy. So the question that we asked is, why is this the case, right? Can we understand why is there this gap so we can help kind of close it? So, okay, so these are the two chips, and again, they're in the same process technology. You can see that our gate counts are pretty much the same. Here, we're primarily in the HOG chip. We're looking only at the feature extraction part, not at the classification part. You can see that the memories are also around the same, and again, we tried to keep it to be the same cost as video compression. Okay, so the first thing is throughput. Let's look at throughput. So we can see that the HOG throughput, it runs at HD 30 frames per second, so it's 62 megapixels per second, but both the AlexNet and the CNN is much, CNN AlexNet or CNN VGG is much lower, and primarily what we try to tease out is what's causing this. So the first thing that we looked at is, what about the number of operations per pixels fundamentally that comes with the algorithm, nothing to do with the hardware, right? And so you can actually see that we're talking about maybe like, almost a little bit over an order of magnitude increase for AlexNet, and then 2 orders of magnitude increase for VGG relative to HOG. And so if we divide this out in terms of the throughput, if we just look at GOPS, just raw GOPS, then they're about the same. It's not too bad. Like VGG is a little bit worse because of maybe the mapping a little bit, but in general, on average, it's the same. So we can say that the throughput difference is primarily due to the difference in number of operations per pixel. But what's interesting is when we start looking at energy. So we have the same thing here. Energy is a 0.5, and then 100 and 6,000 nanojoules per pixel for the other two. We divide out by the operations per pixel, and then we can see here that actually it's still substantially, HOG is substantially more energy efficient. So here, the higher the better than both CNN for AlexNet and VGG. Another side mention, this is a little bit slightly less related, but if we look at DRAM access going off chip, we can also see it's ridiculous in terms of how many bytes you have to read per pixel for both VGG and AlexNet. So the main point I have here is that there's a significant energy gap, and the GOPS don't explain it. So where does this actually come from? So the GOPS, we saw that it's about 30x and 800x difference, but actually the main reason is that CNN requires a programmable architecture. And why is this? So for example, if we look at AlexNet as an example, for just the convolutional layers, they're looking at 2 million weights, right? Assuming about a byte per weight, and you have an area budget of 1,000 K gates and 150 K bytes, if you hardwired all the weights, you're like, okay, forget about this programmability, right? And you just hardwired everything. You could only fit within this area budget about 10,000 multipliers with fixed weights. So that means that you'd have to increase your area size by over 2 orders of magnitude to get the same, to fit the same size. In the other case, like, okay, why don't we just say we're going to keep all weights on chips so we don't have to worry about the data flows and all this kind of stuff. We can kind of hardwire that. And even then, you're talking about a 10x increase in terms of storage. So the main issue is because you need to have programmability if you're going to support these very large networks on a very small piece of hardware. And of course, for CNNs, you also support different shapes per layer and different weights. So depending on your applications, you want to be able to program your weights, where you typically don't do that for the HOG. In terms of how can we close our gaps, okay, there's many different approaches. Again, they're listed in our paper. One popular thing is reducing bit width. We know that Google's TP is only 8 bits. There's also binary filters. I'm going to spend a little bit of time on pruning. So one thing you can do is remove weights, make the weights more sparse, and there's been a lot of work on this. For example, from Stanford, they looked at pruning based on the magnitude of the weight, removing small weights. But in our group, we were trying to think of, well, we'd actually want to target specifically energy, not just like number of weights. So, you can look at accuracy, you can measure it based on a data set. If I gave you a DNN, you can measure speed, kind of estimating, look at number of max, size of the memory, number of weights, but how do you measure energy? So we actually came up with an energy evaluation methodology tool so that you can put in, basically your weights, and then the shape of your CNN, push it through, and it'll tell you what the energy consumption is. Okay, so if you guys want to look at this, it'll be on the Eyeriss website. And so from this, what you actually get is the energy consumption versus accuracy. And shown here, so in the blue is just the dense networks. So the steeper the slope, the better. Shown here in the green is if you pruned it based on the magnitude of the weights. And then shown in the red is if you pruned it based on energy. And you can see that you get over 74% better energy for the same accuracy if you accounted for energy directly, not just looking at size of weights. So to summarize, we know that CNN gives about 2x higher accuracy for orders of magnitude increase in energy compared to HOG. This is primarily due to the fact that CNNs require more operations per pixel, but also because you need a programmable architecture to manage that very large network. And one way to close it is by looking at joint algorithm hardware co-design. And so for more information on this really fast, you can go to the Eyeriss website. And then we also have kind of an overview paper on this whole area that's up on archive that covers all of this stuff in much more detail. You can go slowly. Thank you.